All right. So, suppose that 49% of students at Emory High qualify for free or reduced lunch. We plan on conducting a survey containing a simple random sample of 65 Emory High students. Okay, so if we all do this sample, what do we expect the center of our sampling distribution to be? So we're going to do a whole bunch of samples, and when we're done, the sampling distribution should be normal, right? Every sampling distribution is normal, even if the data is not normal. Okay, so this should build a nice normal curve. What would we expect the center of that curve to be? It should be 49%, because that is the population parameter. Okay, so what is the standard deviation of the sampling distribution? How do we find that? How do we find the standard deviation for a sampling distribution for proportion? Excuse me. Well, we use that formula. The square root of pi times 1 minus pi over n. Okay? So David's asking about the n minus 1. That is the calculation formula if for quantitative data. So you find the differences, you square them, you add them together, you divide by n minus 1, and then you take the square root. So yeah, that doesn't apply here. So we're going to do the square root of 0.49 times 0.51 divided by, how many people are going to be in our sample? 65. So the standard deviation of the sampling distribution is 6.2%. Okay. So the SD here is 6.2%. Does that mean that everybody in the sample, that 68% of the people in the sample are between 6.2 plus 6.2 and minus 6.2? No. This is categorical data, right? When we ask this question, the only responses are going to be yes or no. So the standard deviation does not describe the population at all in this case. Now, if we were asking height or weight or age or something like that, the standard deviation would make more sense in terms of the population. But because this is categorical data, that 6.2% only talks about the variation in our samples, our predicted variation in our samples. Does that make sense? Okay, so create a 2 standard deviation above and 2 standard deviation below interval. So I want to go over 2 standard deviations here and 2 standard deviations here. So I'm going to do 49% plus 2 times 6.2, and I'm also going to do the minus version of that. So 49 plus 2 times 6.2 and 49 minus 2 times 6 plus 2. And I get this interval 36.6% up to 61.4%. So what does that interval mean? That's question 4. What is this a confidence interval? We'll get to that in a second. Is this a confidence interval? So a confidence interval says I'm 95% confident that the true proportion is inside this window. Well, is the true proportion inside this window? Yes. Because We know the true proportion is 49%. So this is not a confidence interval. So what does it describe? I almost said subscribe. What does it describe? What does a 2 standard deviation window on the sampling percentage tell us? Okay, now you can answer. It's 95% of all samples. So if 100 people take samples, 95 of them should have a proportion that lands in that window. Okay? That is a probability, essentially. If you take a simple random sample, you have a 95% chance of landing in that window with your sample proportion. Okay? Does that make sense? So, here is the question. We used this formula. That formula is using the the population parameter pi, the true value. Where did this come from? I went down to the office and I said, what proportion of our students are on free and reduced lunch? And actually I just made the number up because I was too lazy to go ask. It's probably, it might actually be higher than 49%. Okay? Is there any error in that data? No, because we asked every kid, right? The office knows if every kid is on or not on free or reduced lunch. Okay? So, if we take a sample, we are going to get a p hat. And we are going to use this formula to calculate the standard deviation of that sample. And what do you notice? It's the exact same formula. But these numbers have different names. Okay? This is the standard deviation of the sampling distribution. So the pi formula is the standard deviation of the sampling distribution. I'll give you a second to write that down. Sure. You want a paper? Let's give you a paper. You are welcome. You should have brought me a donut. Okay. And the sampling distribution is sort of this theoretical idea of every possible sample that you could take. What happens when lots and lots of people take samples? It's going to look like the sampling distribution. Okay? So this, don't write this down yet, that is a standard deviation that is based off of a single sample. And because of that, we don't call it a standard deviation. Okay? We refer to this as the standard error. Go ahead and write that down. Standard error. So when you take a single sample, so let's say this is your sample, you essentially have one number, a percentage. In that case, it could be like, I don't know, 42%. So you do a sample and you get 42% of your sample is on free or reduced lunch. Okay? Well, we use the standard deviation formula to get this number that gives us what we call the standard error. And the standard error helps us understand how far off our sample might be based off of the results of the sample and how many people are in the sample. And it's the exact same calculation as the standard deviation of the sampling proportion distribution. Okay? So what do we do with that standard error? And we've actually already done it before. We can use that standard error to create a confidence interval. So that formula gives us an understanding of how far off our answers might be. Okay, so next question. Suppose you take a sample of 65 students and you find that 45 of them are on free and reduced lunch. How do we calculate our value for p hat? It's just going to be 45 divided by 65. Our p hat, let's just round it to 69%. Okay. Did our sample proportion fall within the 2 standard deviation interval for our sampling distribution? Let me go back. I erased it. So, right here. Did our sample fall inside that window? It did not. Okay. Does that mean that the original 49% was wrong? No, the 49% is right. It just means we got a sample that was way out there. And sometimes that happens. Okay. What is the standard error for this sample? So we're going to do the square root of 0.69 times 1 minus 0.69 over 65. So what is that? 3.1, not 3.7, 3.1 divided by 65. And I get 5.7%. And again, you can calculate these. You can display these in either percentages or decimals. But when you use this formula, you have to use decimals. If you use percentages, it's going to give you an error every time. Well, I guess not every time, but you definitely don't want to. All right, so how do we calculate the 95% confidence interval? We take our sample percentage, 0.69, plus or minus, how far out is our 95% window? 2 standard errors, so 2 times 5.7, or 0.57, I guess. So 0.69, oh boy, 0.69, I'll get it eventually, plus 2 times 5.7, nope, 0.57. I'll get there. Oh my heavens. Is it Monday? 0.57, there we go. And then the same calculation with a subtraction in there. So I am 95% confident that the true percentage is somewhere between 57.6% and 80.4%. So number 10, did the confidence interval contain the proportion of the population? What was the population proportion? 49. 69 was our sample, 49 was the parameter. So did we capture the parameter? No. What does that mean? Is the parameter wrong? No. It just means we got a sample that was weird. Maybe it wasn't random, or maybe it was random and it just happened to be that we were that far off. Okay. I want you guys to do oh hey, there's supposed to be another L right there. I want you guys to do this next section, and I want to pay particular attention to number 17. Don't look at the back until you finish 17. I want you to really think about that one. So I'll pause the video. When you guys are done with that page, don't go on. I'll come back and we'll go through each answer. Number 11, what was your value for p hat? 30, what was it, 30? Oh, 44.6. I heard wrong. Sorry. So 44.6. Does that fit within 2 standard deviations of the sampling distribution? Yes, it does. Okay. What is the standard error? 6.1%. Okay. So what did you get for a 95% confidence interval? 32.62. Okay. Does that capture the true proportion? Yes, it did. So 16. If the 2 standard interval for the sampling distribution covers our value for p hat, is that a guarantee that the confidence interval for p hat will contain the true proportion? No. Why not? Okay, there's no guarantees in stats. We don't ever guarantee anything. But that's not why. It would make sense, right? If you if you knew the sampling, or sorry, if you knew the parameter and you knew 95% of all values should land in this window, then it makes sense to turn around and say, if you have a p hat that lands in that window, that's a guarantee that the confidence interval for that p hat will also contain the population parameter. And the reason that's not true is our standard error changes based on our sample proportion, right? Our standard error is based on our value for p hat. We're still dividing by 65 no matter what, but our value for p hat will change. As the value of p hat varies, the standard error also varies. So it's not a guarantee. They don't really make sense. If you do land in the 2SD window, you're probably going to have a correct confidence interval, but it's not a guarantee. Okay. I love this question. Why do we use standard errors for confidence intervals and hypothesis tests instead of using the standard deviation of the sampling distribution? You guys looked at the answer, right? How often do we know the parameter? Not often. And when we do, what's the point of doing a sample? If you know pi, why would you take a sample? Right? So going back to this situation, if you knew that 49% of Emory High was under free and reduced lunch, why would you go talk to 65 kids and see if they are on free or reduced lunch? That just doesn't make much sense. It makes a lot more sense if you said, I don't know the parameter, and I don't have time to talk to everybody, so I'm just going to talk to 65 kids. I'll use that to create a confidence interval, and that will give me an idea of what the true value is. Okay, turn the page. You're going to love me. Suppose that 11% of students at Emory High choose to graduate early. So we'll say in the last 10 years, 11% of all students have chosen to graduate early. We plan on conducting a survey containing a simple random sample of 90 EHS students. What is the expected center of our sampling distribution? 11%. That's what the population is, so we would expect the sample to be similar to that. What is the standard deviation of our sampling distribution? So we're going to do 0.11 times 0.89 over 90, and then take the square root of that. Okay, and I get, we'll call it 3.3%, so 0.033. So create an interval that is 2 SDs and 2 above and 2 SDs below the sampling distribution. So 0.11, oh, I keep forgetting, plus 2 times 0.033, and then the same thing with the subtraction. And that is going to give me everything from 4.4% to 17.6%. Okay. So then we're going to open up our app, which I think I've done. Okay. And right here on the right side, we're going to click on one proportion for inference. Okay. And we are going to do 40 individual samples. How do we do that? Well, what do we put in as our probability of heads? 11%. How many kids are we going to talk to? 90. And we don't want to do 40 samples all at once, because I need to know, well, you need to know, the individual result from each sample. So I'm going to leave this at 1, and I'm going to click Draw Sample. What happened? I drew a sample, and I got, right here, I got 6. So I'm going to go back to my worksheet. Not that one. This one. Let's see if we can do, this will make more sense. Okay, so, nope. What did I do? Oh, there we go. So, in sample 1, I got a 6. And then I need to do 6 divided by 90. And I get 6 point, oh, I need a pen. I got 6.6%. Then I go back and I run another sample. It's not letting me go back. I broke it. Ralph broke the internet. Okay, so then I run another sample, and right here I get 7. So over here, I write 7, and then on my calculator, I do 7 divided by 90, and I get 7.7%. Okay, so you guys need to go through and do, oh, that's not what I wanted. And do all 40 samples. No, I'm serious. All right, but look at 23. 23 says, hold on, pay attention to this. Almost. He's almost paid attention. Oh. So 23 says, how many of the 40 samples did we expect to be within 2 standard deviations of the population proportion? That would be 95% of 40, right? What is 95% of 40? 38. So the answer for 23 is 38. And then you're going to go through and count how many landed in that window. So the window was from 4, sorry, I can't write from my desk very well, 4.4 to 17 point something, right? Is 6 in that window? Yes. Is 7.7 in that window? Yes. So you need to go through and count how many were in that window. We expected 38, and then you're going to count them. Okay. Some of you are working ahead. Hold on, stop for a second. Then we're going to go down here. You're really going to love me. You need to create confidence intervals for all 40 samples. Does that sound like fun? No. So we're going to cheat. So go back into Rossmann and go to theory-based inference right here. And then instead of test of significance, we're going to run a confidence interval. And my sample size is 90, and my count was 6. calculate, there's my confidence interval. So I write that down. And then my second count was 7. Calculate, there's my confidence interval. Did this confidence interval capture the true value? What is the true value? 11%. Does this confidence interval capture 11%? Yes. How many of those 40 do we expect to capture the true percent? 38. So it's actually not too bad. You can let the computer do most of the work. Okay, you have the rest of today to finish this. Get to work.